capacity, and we have seen how they are connected by the equation Cp minus Cv is equal to R for an ideal gas. Now, in this class, we will talk about calorimetry and an instrument which is called as bomb calorimeter, and we will see how we can physically measure the these parameters delta U and delta H, that is change in internal energy and change in enthalpy of an ideal gas. Now, so with this, we will start our today's discussion. So in this class, as I have told, we will talk about calorimetry. Now, there are many types of calorimetry. We can measure the change in energy that is associated with any chemical or physical process by this experimental technique. So by calorimetry, we are able to measure or calculate the change in energy, that is enthalpy or internal energy. Now, in calorimetry, the process in which the procedure is actually carried out is called as a calorimeter. Now, in calorimeter, it is immersed in a known volume of liquid. You can see over here, it is a known volume of liquid. Let me just bring up the pointer over here. Yeah. So in this case, you can see the thermometer to detect the change in temperature. This is the starter, and these are the ignition wire. This circular kind of thing is called the bomb. That's why it is called the bomb calorimeter. Now, it is used to measure the heat of a reaction when the volume is actually kept constant. The volume is kept constant. That's why it is called the constant volume calorimetry. Now, it is also immersed in a known volume of liquid. Knowing the heat capacity of the liquid in which the calorimeter is immersed. So, heat capacity of this liquid over here, should be known to us. And also the heat capacity of the calorimeter too. So now we are able to calculate or determine the heat that is evolved through the process by measuring the changing temperature. Because according to our equations that we are talking about in the last class, Q is equal to, Q means the heat capacity, Q is equal to C into delta T. So if we have an idea about the value of C, and if we can calculate the change in of temperature of the system by using this thermometer, the thermometer shows us the change in temperature. And if we know the heat capacity of the system, then we can calculate Q as C into capital delta T. The measurements are typically carried out under two different conditions. First one is at constant volume, and the second one as the constant pressure. So QP will be Cp into delta T, and QV will be CVP into delta T. So at constant volume, it can be carried out, or it can also be carried out at constant pressure. Now, although there are many aspects of bomb calorimetry that are made for accurate results, they also contribute to the difficulty of the bomb calorimetry too. So now we will address what is the basic assembly of a bomb calorimeter, and that is why how it can relate to the heat of the reaction, also the heat capacity, and what are the calculations that are involved regarding these three topics. Now, as you can see over here, in calorimetry, it is used to measure the heat quantity and can also be used to determine the heat of a reaction through instruments and experiments. Now, usually in a coffee cup calorimeter is used since it is much simpler than a bomb calorimeter. But to measure the heat that is getting evolved from a combustion reaction, that is Q. So in this case, we will have a coffee cup calorimeter. A constant volume calorimeter is also more accurate than the coffee cup calorimeter, but it is more difficult to use since it requires a well-built reaction container setup. and that can withstand very much large amount of pressure change that can take place in many chemical reactions. Now, for any chemical reaction, the absorbed at a constant volume is measured in a bomb calorimeter. Now, here we are talking about a steel vessel, that is the bomb, that is immersed in the water bath. This is the bomb. The steel vessel is immersed in a water bath to ensure that no heat is lost to the surroundings. And to ensure no heat is lost to the surroundings, it is kept inside an insulator. So, this outer coating or wall you are looking at is an insulating setup. The insulator. Now, a combustible substance is actually put inside the steel bomb, and it will be burnt in pure dioxygen that will be supplied to the bomb. It is inside the bomb. So, in pure dioxygen, the complete burning of the sample will happen. Now, heat evolved during the reaction is transferred to the water around the bomb, and its temperature is monitored. So, inside the bomb, the reaction will take place. This is the sample holder on which we will put the sample. And when the sample is kept over here, this is the stirrer which will keep stirring the water so that the homogeneity of the temperature throughout the water is maintained. And now, when in pure dioxygen, the sample is completely burnt off, the heat that will be generated from the reaction will be transferred to this water that is surrounding the bomb. And when the water is completely taking up the heat that is lost from the bomb, it will be calculated. The change in energy or temperature will be calculated by this very thermometer. Since the bomb calorimeter is sealed, it is completely sealed, the volume of the setup will not change. The volume will not change. The energy change that will be associated with the reaction, so it will be calculated at a constant volume, since delta V will be zero over here. So this is such a physical process where it is completely sealed, and delta V will be equal to zero, and the energy changes that will be associated will be under constant volume. So we will calculate the heat that is evolved from the reaction as QV. V suffix means the volume, or V is kept constant. So we will calculate the CV over QV over here. Since there is no change in volume, so there will be no work done, because W, that is work done, is nothing but minus P external into delta V. And since delta V is equal to 0, so W will be equal to 0. So delta U is equal to Q plus W. From the first law of thermodynamics, we know delta U is equal to QV. So delta U actually now falls to QV because W is equal to 0. So since it is a constant volume in the bomb calorimeter, so inside a bomb calorimeter, whenever you are asked what is the work done, it will be equal to 0, since the no change in volume is taking place because of the sealed environment, and QV will be equal to delta U. Now, even for reactions involving gases, whatever the sample will be inside it, or if it is solid or liquid, it does not matter. Even when the samples we are talking about are gases, in that case also, we will see temperature will be no work because delta V will be equal to 0. Temperature change of the calorimeter will be produced because complete reaction is taking place and is then now converted to QV by using the heat capacity of the calorimeter with the help of the equation Q is equal to C into delta T. So now we can calculate the heat generated from the reaction as QV is equal to CV into delta T. That will be our main equation to calculate the QV. But also in this case, we can calculate delta H. Measurement of heat change at a constant pressure, that is QP, will be determined here. As you know, delta U is equal to QV and delta H is equal to QP. So at constant pressure, it can be done inside a calorimeter. So heat absorbed or evolved, that is QP at constant pressure, is also called the heat of reaction or enthalpy of reaction. So heat evolved at a constant pressure, or that is atmospheric pressure, is called the heat of the reaction or the enthalpy of the reaction. So we have QP over here, which is delta H. Now QP or delta H, that is at a constant pressure. Now if for a constant pressure the heat is evolved or absorbed during the reaction course, it is also called the del RH. That is the heat of the reaction. For practical purposes, you will see the reactions we perform in the laboratories are all done at a constant pressure, not at a constant volume. So in that case, these reactions are carried out at a constant pressure. That's why it is called the del RH, that is the heat of the reaction. And so it is for the reactions we carried out in laboratories are called QP. For an exothermic reaction, heat will be evolved. So the system will lose heat to the surroundings. Therefore, if system is losing heat to the surroundings, then QP will be less than 0. For exothermic reaction. And similarly, if in an endothermic reaction, if heat is absorbed, so the system is absorbing heat from the surrounding, then QP will be greater than 0. So for an endothermic reaction, QP as well as delta H will be greater than 0. And for an exothermic reaction where heat will be evolved during the process, QP and delta H will be negative. That will be an exothermic reaction. The calorimeter for which we will, or the at a constant pressure, we will calculate the heat change. So in that case, there will be a formed polystyrene or polymer kind of cup. And inside the cup, there will be a reaction mixture. And a thermometer will be introduced inside it to check the temperature change of the reaction. And now by this process, it is a constant pressure calorimeter. We will calculate the change of the temperature by thermometer, and then by using the equation Q is equal to T into delta T, we will calculate the delta H of the reaction or the heat of the reaction. So in this slide, I have constructed the bomb calorimeter that we discussed in the last class, and there will be some specific components of a bomb calorimeter. First of all, it will be a steel bomb which actually contains the reactants. Inside the bomb, the reaction will go on. There will be a water bath in which the bomb is submerged or immersed. There will be a thermometer to calculate the temperature change. There will be a mortar starter to maintain the homogeneity of the reaction mixture or the water, and there will be wire for ignition. So the sample could be burnt in complete oxygen atmosphere. Now, most serious calorimetry that will be carried out in these laboratories will have to determine the heat of combustion or delta H combustion, since they are essential to determine the standard enthalpy or formation of many new compounds. that are prepared and characterized. So at a constant volume calorimeter, the system is sealed or it is completely isolated from the surroundings, which confirms that the volume is fixed and no volume pressure work is done over here. As you see over here, the complete container is sealed, so there will be no change in the volume of the mixture or the system. And then if we calculate the heat of combustion, that is delta H combustion, so there will be very much essential to determine the standard enthalpy of formation of thousands of new compounds. So in that case, since the volume is fixed, there will be ensuring that there is no volume pressure work done. So PV work will be equal to 0. So in a bomb calorimeter, there are these 5 components that will be measured, as I have mentioned. First one is the circular steel bomb, because of which it is termed as bomb calorimeter. A water bath, inside which the bomb is immersed. A thermometer to calculate or measure the temperature change. A motorized starter, and a wire for ignition. Now, since the process is taking place at a constant volume, the reaction vessel must be constructed that it can withstand very high pressure, because of the combustion process, many gas will be evolved that will actually increase the pressure inside the valve, because you see it is a sealed container over here, and inside this sealed container I will generate more amount of gas by combustion. So the pressure of the gas will must be high, it will go high. But since PV is equal to constant and V should be maintained constant in this case, so very much high pressure will be built up because V is constant inside a bomb calorimeter. Now P will be very much high. The gas pressure that is generated inside the bomb calorimeter will be much high. The high pressure will result from a combustion process and which can actually result in a confined explosion. So inside this container, an explosion can take place if we do not introduce such a material that can withstand very high pressure. Now the reaction, the vessel is actually called as a bomb, and so the technique is called the bomb calorimetry. The reaction is initiated by discharging a capacitor through a very thin wire which ignites the mixture. You see over here, an ignition wire are actually shown over here. So inside this there will be capacitor which will start igniting the reaction mixture. Now another consequence will be there will be constant volume condition. So the heat released corresponds to QV, and thus the internal energy change delta U rather than to delta H. So delta H, the enthalpy change is calculated according to the formula delta H is equal to delta U plus delta Ng RT. So delta U is equal to QV because it is a constant volume reaction, and by substituting PV by delta Ng RT. Delta Ng is a change in the number of moles of gaseous components of the reaction. In the last class, I have told you why we will be talking about only the change in number of moles of gas components only, because in case of solid and liquid components, the volume change is very much negligible. But in case of gas, it will be very much high. So we can neglect the change, that is delta Ng, of delta NL, that is liquid, and delta NS, that is solid. So delta Ng is the change in the number of moles of gaseous components of the reaction. The equation that will be used by us in this course is delta H is equal to QV plus delta Ng RT. Now we will have seen that how are the parameters defined over here, and we'll see now how we can calculate the procedure of delta H and delta enthalpy in a practical solution. So there is a problem. A sample of biphenyl, that is C6H5 is weighing around 0.526 gram at room temperature, that is 25 degrees Celsius. It is kept inside a bomb calorimeter. Now it is producing a temperature rise of 1.91 Kelvin. So in a separate calibration experiment, a sample of benzoic acid that is C6H5COOH, weighing around 0.8 to 5 gram, was ignited under identical conditions, and it produced a temperature rise of 1.94 Kelvin. Now, for benzoic acid, the heat of combustion at constant volume is known to be 3200 at 26 kilojoule per mole. That is, delta U is minus 3226 kilojoule per mole. So use the information to determine the standard enthalpy of combustion of biphenyl. So here we will start by working out the calorimeter constant. So we will begin by working. Firstly, we will calculate the moles of benzoic acid. We have seen that benzoic acid is weighing 0.825 gram. So this is the structure of benzoic acid. We have a phenyl ring, and with which we have a COOH. So this is benzoic acid, and the weight of benzoic acid is 825 milligram. Now, if we calculate the moles of benzoic acid, it will be 0.825 gram divided by its molecular weight. It is 122.1 gram per mole. So this is the weight given, and this is in the denominator, we have the molecular weight of benzoic acid. So if we perform the calculation, we have the number of moles as 0.00676 mole. Now, what is the heat released to the calorimeter? You see, for benzoic acid, the heat of combustion at constant volume is 3226 kilojoule per mole. So, for per mole of benzoic acid, the heat release is 3226 kilojoule. Now, for 0.00676 mole, the heat released to the calorimeter is multiplication of these two, because 1 mole corresponds to 3226 kilojoule. So for this much amount of mole, the heat released will be 0.00676 multiplied by 3226 kilojoule per mole. That is the heat of combustion of benzoic acid, which is 21.80 kilojoule. Now, 21.80 kilojoule of heat is released for this much amount of benzoic acid, and the temperature rise is 1.94 Kelvin. So the calorimeter constant will be the total heat released to the calorimeter, that is 21.80 kilojoule, divided by the temperature that is present. So calorimeter constant C will be Q by delta T. So this equation is used over here. So it will be 21.80 kilojoule divided by 1.94 Kelvin. That will be 11.24 kilojoule per Kelvin. Now we have all the constants regarding the benzoic acid over here. Now, since we have got the calorimeter constant from the data derived from the benzoic acid, we will have to calculate the delta U combustion of the biphenyl system, which is BP. So biphenyl structure are two phenyl rings connected to each other by a CC bond. This one is biphenyl. So for biphenyl, we will also calculate the moles of moles. Here it is given that 0.526 gram of biphenyl is here. So here also we will calculate the moles of the biphenyl, 0.526 gram divided by the molecular weight, that is 154.12 gram per mole. Number of moles will be 0.00341 mole. Now the heat released to the calorimeter will be 1.91 Kelvin, because this is the heat released, which is shown over here, 1.91 Kelvin. And since the calorimeter constant we have got from the last equation of benzoic acid, that is 11.24, we have the heat released to the calorimeter as 21.46 kilojoule. Now heat released per mole of biphenyl will be 21.46 kilojoule, divided by the number of moles, that is 6293 kilojoule per mole. So delta U combustion of the system will be minus 6293 kilojoule per mole. So this delta U combustion is the heat change at constant volume. The negative sign indicates the reaction is actually exothermic, as all the combustion reactions are exothermic. So delta U will be minus 6293 kilojoule per mole. So the reaction is shown over here. We have biphenyl C6H5 whole 2, that is solid, plus oxygen will be producing CO2 and H2O. So if we try to balance this equation, we have C6H5 whole 2, which is biphenyl. It is combusting in air or oxygen. So any combustion of any hydrocarbon will lead to CO2 and gaseous CO2 and water. So if we have to balance this equation, firstly we will have to see what are the components we have to consider over here. Firstly, we can start with balancing the carbon. Here on the left hand side we have 12 carbons, on the right hand side we have only one carbon. So if we have to balance this, we have to multiply this side as 12. So if we write 12 ahead of CO2, the number of oxygen atom becomes 12 into 2, that is 24, plus this water oxygen, that will be 25. But here we have O2, so only 2 oxygens. We can also start with this hydrogen also. We have 10 hydrogens on the left hand side, and on the right hand side we have only 2 hydrogens. So we have 10 over here, we have 2 over here. So we can start writing 5 over here. So it will be 10 hydrogens. So if 10 hydrogens is there, so 10 hydrogens and 12 carbons are matching on the both sides. But we have to balance the oxygen also. So the total number of oxygens is 12 into 2, that is 24, plus 5, that will be 29. So here we have 2 oxygens. So to balance this equation, we have 29 by 2 will be here. So why we need to balance this equation? Because if we do not balance the equation, we won't be able to calculate delta Ng, that is change in the number of moles of gaseous components of the reaction. So to calculate the number of moles of the gaseous component, we have to calculate delta Ng. And to calculate delta Ng, we are trying to balance this equation. So we now finally have balanced. Now on the right hand side, water is liquid, but on the left hand side, biphenyl is solid. The gaseous components are CO2 and O2. So if we calculate delta Ng, that is change in the moles of the gases of the reaction, we have delta Ng equal to 12 minus 29 by 2. That will account for minus 5 by 2 or minus 2.5. Thus the volume of the system is actually decreasing when the reaction is taking place. Now if we convert it to delta H, we can write the following equation. Additionally, we can also remember the fact that delta U is equal to QV. From this equation, we have got the delta U combustion, that is minus 6293 kilojoule per mole. Now we can calculate the delta H from over here. Delta H will be delta U plus delta Ng into RT. So delta U can be written as QV or delta U. Delta U is given as minus 6293 kilojoule per mole. And in this equation, delta Ng RT, we will substitute delta Ng as minus 5 by 2. R value will be 8.314 joule per mole per Kelvin. And we have the temperature set at 298 Kelvin, that is 25 degrees Celsius. Now we have from the left hand side, we have minus 6293 kilojoule per mole. And on the right hand side, it is calculated will be joule. That you have to remember the fact that the delta Ng RT will be calculated in terms of joule, but delta U is given as kilojoule. So we cannot add those two components simply. We have to first convert this joule to kilojoule. So the joule value is minus 6194. So if we convert it to kilojoule, it will be minus 6.194 kilojoule per mole. So if we add these two, 6293 and 6.2, we have got minus 6299 kilojoule per mole. That's why I've written over here. There is a common mistake over here, that is to forget that a subtraction is formed. The subtraction of, in this case, delta QV will be in terms of kilojoule, but delta NGRT will be calculated in terms of joule. The additional 6.2 kilojoule in delta H compared to delta U reflects that is work that the surrounding is doing on the system, as the volume of the gas is decreasing according to the reaction equation. Here you can see delta U value is 6293 kilojoule per mole, but the extra 6.2 kilojoule per mole of delta H is also introduced. That introduction comes from the fact that the surroundings is performing some work on the system. That's why the volume of the gas is decreasing. That's why the delta Ng that we calculated over here is negative over here. If delta Ng is positive, that means number of moles of the gas is increasing. So there will be an increase in volume. But when delta Ng is negative, that means the gases are compressed. And who is compressing the gas? The gas compression is taking place because the surroundings is performing some amount of work on the gas. That's why the volume of the gas is decreasing. The reaction equation says delta H will be minus 6299 kilojoule per mole. From this, we can determine the heat of the reaction also. The amount of heat that the system loses to the surroundings, so it can return to its original initial temperature, is the heat of the reaction. The heat of the reaction is thus the negative of the thermal energy gained by the calorimeter and its contents. So Q calorimeter can be determined over here to the combustion reaction. So the Q reaction will be minus of Q calorimeter, where Q calorimeter is equal to Q of the bomb and Q of the water. See over here, if it is a sealed bomb calorimeter and inside this we have a liquid and a bomb over here. Now we have this Q calorimeter. Q of this calorimeter will be minus Q of the reaction. Inside the bomb, the reaction will take place. Now Q bomb plus Q water is the total amount of Q of the calorimeter. If the constant volume calorimeter is set up the same way as before, same steel bomb, same amount of water, everything will be kept same, then the heat capacity of the calorimeter can be measured using the formula. Q calorimeter is equal to heat capacity, or C of the calorimeter, into delta T. So the heat capacity is defined as the amount of heat needed to increase the temperature of the calorimeter by 1 degree Celsius. The equation above can also be used to calculate Q reaction from Q calorimeter according to the equation 2. The heat capacity of the calorimeter can be determined by conducting an experiment. We will move to the next problem, by which your understanding of calorimeter will be easier. So we have 1.15 gram of sucrose that is going through combustion in a bomb calorimeter. So we have a bomb calorimeter, and inside the bomb we are burning off 1.15 gram of sucrose by simple combustion. So if the temperature is rising from 23.42 to 27.64 degrees Celsius, and the heat capacity of the calorimeter is 4.90 kilojoule per degree Celsius, to determine the heat of combustion of sucrose, that is C12H22O11 in kilojoule per mole of sucrose. Now we will see what are given to us. So any numerical problem, if you start to solve, firstly you have to look that what information is given to you and what you can determine. So firstly we have 1.15 gram of sucrose. We have the T1, that is T initial, as 23.42 degrees Celsius. This is T1. And we have T2 as 27.64 degrees Celsius. The heat capacity of the calorimeter is 4.90 kilojoule per degree Celsius, which is written over here. So these four things are given to us. Now using equation 4, we can calculate Q calorimeter. In this equation, you see this equation 4, the Q of the calorimeter is heat capacity of calorimeter multiplied by delta T. So we have Q is equal to heat capacity, that is 4.90 kilojoule C of the calorimeter multiplied by delta T. So delta T is 27.64 minus 23.42, which is around 4.22 degrees Celsius. And we have the Q calorie of the constant heat capacity of the calorimeter as 4.90 kilojoule per degree Celsius. So simply we'll multiply 4.90 and 4.22. We have 20.7 kilojoule. Now we have 20.7 kilojoule, which is the Q calorimeter. We know Q reaction is actually negative of the Q calorimeter. So Q reaction will be just the negative value of the Q calorimeter. So Q reaction will be minus of 20.7 kilojoule. But the question we are asked about is the kilojoule per mole of the sucrose. So for this, we have to convert this value to the moles. Now Q reaction will be minus 20.7 kilojoule divided by 1.150 gram of sucrose. So we'll divide 20.7 by 1.15, that is yielding to minus 18 kilojoule per gram of sucrose. Now from gram to mole we have to go, because the question we are asked about kilojoule per mole of sucrose. So we have a Q reaction as minus 18.0 kilojoule per 1 gram of C12H22O11 multiplied by 342 into 3 gram of sucrose divided by 1 mole of this thing. So if we have 342 into 3 gram, that is correspond to 1 mole. 342.3 gram corresponds to 1 mole of sucrose. So 1 gram corresponds to 1 divided by 342.3 moles of sucrose. So in this 1 gram, we can substitute by 1 by 3.342.3. This 342.3 will go to the numerator, and we have minus 18.0 into 342.3. So we have the multiplication minus 6.16 into 10 to the power 3 kilojoule per mole. So finally, we have got the answer that in case of the sucrose burning, the determinant of heat of combustion of sucrose, that is Q of reaction, will be around minus 6.16 into 10 to the power 3 kilojoule per mole. So we have these reactions over here. So in the next problem, we will see how other problems can be solved in case of bomb calorimeter 2, so that a better understanding is given to you. So we have 1 gram of graphite over here. 1 gram of graphite is actually here, and it is kept inside a bomb calorimeter, and it is burnt in excess of oxygen at 298 Kelvin and 1 atmospheric pressure. So if graphite is burnt, so C solid, that is graphite, it is burnt in oxygen, which is a gas. And it forms CO2, that is carbon dioxide. Now during the reaction, the temperature rises from 298 Kelvin to 299 Kelvin. So we have T1 as 298 Kelvin. the initial temperature. And we have T2, the temperature change is only 1 Kelvin. So T2 will be 299 Kelvin. Now, if the heat capacity of the bomb calorimeter is 20.7 kilojoule per Kelvin, the heat capacity of the calorimeter. So C of the calorimeter is given as 20.7 kilojoule per Kelvin. So 20.7 kilojoule per Kelvin of heat is actually here. And it is the heat capacity of the bomb calorimeter. Now we have to calculate the change of the enthalpy of the entire reaction course, and where we have this following information as at 298 Kelvin is the initial temperature, 299 Kelvin is the final temperature. K C calorie, C of the calorimeter is nothing but given as 20.7 kilojoule per Kelvin. Now we have to calculate the enthalpy change for the above reaction. So suppose we have Q amount of heat that is evolving from the reaction mixture, and Cv is the heat capacity of the calorimeter. Now the quantity of heat that will be absorbed by the calorimeter will be Cq is C of the calorimeter multiplied by delta T. Now quantity of heat from the reaction will have the same magnitude but opposite sign because heat is lost by the system. So the reaction mixture is equal to the heat gained by the calorimeter. So for the reaction, we have Q is equal to minus C calorie into delta T. So we have Q is equal to Q for the reaction is thus the negative value for the Q of the calorimeter. So we have minus of Q calorie, that is C calorie into delta T. So C cal is given as 20.7 kilojoule per Kelvin. And delta T is nothing but 299 minus 298, that is 1. In Kelvin. Sorry, it will be kilojoule per Kelvin and it will be K, so it will be kilojoule. So if we multiply 20.7 into 1, it will be minus 20.7 kilojoule. So Q reaction is minus 20.7 kilojoule. That is an endothermic reaction. So delta U, that is for the combustion of the 1 gram of graphite, will be minus 20.7 kilojoule per Kelvin. Now for combustion of 1 mole of graphite, we have 12.0 gram per mole into minus 20.7 kilojoule. So we have given that 1 gram of graphite is over here. So it is for 1 gram of graphite. But the question asks what is the enthalpy change per mole. So in this case, we have 1 gram. So 1 gram corresponds to how much amount of graphite. So for graphite, the molecular weight is 12. So 12 gram corresponds to 1 mole. We have 1 gram. So 1 gram corresponds to, so this actually corresponds to 1 gram. Graphite's molecular weight is 12 gram per mole. We have 1 gram. So per gram, it will be minus 20.7 kilojoule per gram. So if we convert the gram into mole, similarly as in the last case, we have divided the molecular weight of sucrose. It will be 1 by the molecular weight of sucrose. In this case also, it will be 1 divided by the molecular weight of graphite. So we have the Q reaction is equal to minus 20.7 kilojoule multiplied by 12 gram per mole. For this minus 20.7, we had a unit of kilojoule per gram. This gram inverse and gram will get cancelled out, and we have lastly minus 248 kilojoule per mole. This is minus 248 kilojoule per mole. Now, similarly, that in the last case, we had calculated delta Ng of the reaction, that change in the gaseous component of the reaction. Here also you can see all the components are not gas. So carbon is graphite is solid. It will not be considered. We have two gaseous components, CO2 and O2. So number of CO2 moles is 1 and number of oxygen moles is also 1. So delta Ng in this case will be 1 minus 1. That is 0. So here, since delta Ng will be 0, so we have the equation delta H is equal to delta U plus delta Ng RT. Just like the last equation where we solve for sucrose. Since delta Ng is equal to 0, delta Ng is 0. So delta H will be delta U. And we have calculated delta U as minus 248 kilojoule per mole. So both delta H and delta U will be minus 248 kilojoule per mole. So in this case, since delta Ng is equal to 0, we have ultimately got it that Q reaction is nothing but delta U. And since we have delta Ng is equal to 0, we have delta H equal to delta U. So delta U for the combustion of 1 gram of graphite was minus 20.7 kilojoule per gram. Then we have actually tried to convert this gram to the number of moles to calculate the per mole Q reaction. And since delta Ng is equal to 0, we have delta H and delta U. So for this kind of processes where delta Ng will be equal to 0, so change in enthalpy and change in internal energy of the system will be equal. So here I will give you a brief review of what important things we went through in this chapter, because it involved many kind of calculations over here. So for a typical example, we had first introduced the sucrose example where we are given a number of sucrose molecule of the weight. So whenever you are given the weight, your first job will be try to determine the number of moles of the sucrose. Here we have also calculated the number of moles of the sucrose in the last step, that is 1.15 gram of sucrose over here divided by the number of moles, the molecular weight, that is 342.3. So first you will determine the N, that is number of moles of the substance. In the next example also, we had to calculate the number of moles of graphite, that is 1 by 12. Here the number of moles is 1.15 divided by the molecular weight of the sucrose, that is 342.3. So after calculating number of moles, you have these given equations T1 and T2, because you have to calculate the delta T. Delta T over here was 4.22 delta T in degrees Celsius. So from there we calculated Q calorimeter as 20.7 kilojoule. Since the Q reaction and Q calorimeter will just be the negative sign, because in the previous slide I have told that the amount of heat the system gives up to surroundings so that it can return to its original system, that is called the heat of the reaction. Now the heat of the reaction is nothing but the negative of the thermal energy that is gained by the calorimeter, because inside the calorimeter the reaction is taking place. If the reaction is giving up Q reaction, so the entire amount of Q calorimeter of heat will be absorbed by the calorimeter. So Q reaction is just the negative value of the Q calorimeter. So when you have got the equation Q reaction is equal to minus Q calorimeter, that is 20.7 kilojoule. After we calculated the Q calorimeter, we have to convert it to the moles, because this entire thing was done for 1.15 gram of sucrose. Now we have to use the conversion factor of 1.15 gram of sucrose to the number of moles. So in the last step, they have calculated the number of moles, and just by division of this, we calculated the lastly have calculated the Q reaction. After we calculated Q reaction, you have to remember the fact that also delta Ng can also delta H and delta U can also be calculated for this case also. So in this case, we have C12H22O11. That is sucrose. And it will be burnt off in oxygen to produce CO2 and H2O. H2O is liquid and C12H22O11 is solid. But to calculate the delta Ng value of the reaction, you have to see how this equation can be balanced. In one of the previous slides, I have shown you that how the biphenyl combustion in oxygen can be balanced, and your homework will be to see how this sucrose burning off in air can be balanced. If you can be able to balance this equation, you will be able to calculate the delta Ng of the reaction, which I have not calculated or shown over here. If you calculate delta Ng, now you can easily calculate the delta H, that is change of enthalpy of the reaction, because you have the delta U over here. If you have the Q reaction, so from this, if you can calculate delta U is already given to you, and now you have to calculate delta Ng into RT. R is known to you. Delta Ng will be derived from this sucrose equation. And lastly, we have got the T as the initial temperature, that is 23.42 plus 273 Kelvin. So from there, we will be able to calculate the delta H of the reaction, that is change in enthalpy. So in the last class, I have shown you that from the delta H, you can calculate delta U plus delta Ng RT. Since in this case, it was quite easier because delta Ng was equal to 0. So delta H and delta U were just the same. So ultimately, we are able to calculate the change of enthalpy of the reaction and change in the internal energy of the reaction. So with this, we are drawing a conclusion of today's discussion. In the next class, we will talk about the Dillard H, that is the reaction enthalpy, and different kinds of enthalpy of reaction, different standard enthalpy of reactions, enthalpy change during phase transformation from solid to liquid, from liquid to gas, from solid to gas, and standard enthalpy of formations too. There are different kinds of standard enthalpy change for fusion and vaporization. So we will discuss those in the next class. So if you have any query or doubt regarding any of the slides of today's discussion, you can easily ask.